Hello and welcome to Physics 111 at Dell Tech. My name is Dr. Mark Taylor. This video is one of several short videos designed to review specific math skills that will be useful for this course. This particular video will cover the method called cross-multiplying or cross-multiplication. This is a useful and very fast method that eliminates fractions that might appear in your equations or calculations. These fractions might be on both sides of the equation, or they might just appear on only one side of the equation. And after we go over the method, we'll review a couple examples of how to use cross-multiplying, both with formulas that just have variables, no numbers, and then we'll do a couple examples where we put the numbers in and we'll solve for some unknown variable using those numbers in the formula. Okay, so cross-multiplying, it's a simple and very fast algebraic method that eliminates fractions that appear on both sides or on one side of the equation. And we'll show the example where it's both sides of the equation. So you can imagine a formula where you have one fraction, numerator 1 divided by denominator 1, equals some other fraction, numerator 2 divided by denominator 2. Well, the way to use cross-multiplying is you literally cross-multiply. You multiply the numerator from one side times the denominator of the other side. So numerator 1 times denominator 2. And then you do the other way, numerator 2 times denominator 1. And these two will equal one another. So the two products equal one another. Numerator 1 times denominator 2 equals numerator 2 times denominator 1, and that's shown here. So that's the general method for cross-multiplying when you have two fractions, one on either side of the equation. Now, what if you have only one fraction in your equation? And this actually comes up quite frequently. If you have only one fraction, let's say it's number 1 or numerator 1 equals a fraction, numerator 2 divided by denominator 2. You can still use cross-multiplying to eliminate that fraction. All right, well, how do we do that? Well, consider the fact that any individual number, in this case number 1, n1, is really a disguised fraction. It's that numerator 1 divided by an invisible denominator of 1. Well, you can still do the cross-multiplying like we did before. You cross-multiply numerator 1 times denominator 2, and numerator 2 times this hidden denominator 1, which is just the number 1. And we end up with our result of numerator 1 times denominator 2 equals 1 times numerator 2, or numerator 2 times 1. Well, you don't need the 1 in there. You can just eliminate the 1. And now we have a result of numerator 1 times denominator 2 just equals numerator 2. We just don't bother writing the other denominator, which is just 1. Well, if you have this fraction shown on the left here equal to a single number, so n1 equals n2 over d2, shown on the left, you can still do the cross-multiplying, but the second part of the cross-multiplying shown in blue is really just a single number, times 1, so you don't need to write times 1, and you can just write your answer directly. So you can still use cross-multiplying very easily as long as you remember that any number written by itself is really a disguised fraction where it's that same number divided by 1. So let's take a look how this is used with actual scientific formulas. Here are a couple real scientific equations. This one actually happens to be from chemistry. It's pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. What this really says, and you don't have to know this, is that if you have a gas that has a certain pressure 1 and a certain temperature 1, and you change the pressure or the temperature, you'll get a new pressure and a new temperature, and this equation tells you the relationship between those four numbers. So we have this equation, and you can simplify it to get rid of the fractions by doing a cross multiplying. And you'll end up with pressure 1 times temperature 2 equals pressure 2 times temperature 1. A very famous equation from physics is the speed or velocity equation. In this case, it's written as speed, abbreviated as v, equals distance divided by time. Or you can say velocity equals displacement divided by time. It's actually two related equations, but it doesn't matter. It's the same math. So we have v equals d divided by t. And you can cross multiply to get rid of this fraction. So you multiply v times t, but d doesn't have a partner. It's the invisible 1 that is underneath the v. So it's v divided by 1. So d is times 1, and you end up getting this much simpler looking d equals v times t. Distance equals speed times time, or displacement equals velocity times time, depending on which use you're going to be using in physics. And that's how you use cross-multiplying with real formulas. Now, we haven't stuck any numbers in, but this allows you to simplify the formulas before you put the numbers in. But some people like putting the numbers first. So here's the same P1 over T1 equals P2 over T2 formula, but now I put numbers in. 45 atmospheres of pressure, atmosphere is a unit of gas pressure, divided by 325 degrees Kelvin, that's a unit of temperature, equals 12 atmospheres of pressure divided by our unknown temperature. Well, we could have simplified the formula before we put the numbers in, like we did in the previous slide, or we could put the numbers in and then do the cross multiplying. So you can cross multiply the 12 atmospheres times the 325 degrees Kelvin, and that will equal your unknown temperature, T2, times 45 atmospheres of pressure. So that's shown here. And now you still have to solve for the T2. So in order to solve for T2, you have to divide both sides of the equation by 45 atmospheres. And that's shown here. The 45 atmospheres cancels itself on the left side of the equation. And now we've simplified our equation to temperature 2 equals 12 atmospheres of pressure times 325 degrees Kelvin divided by 45 atmospheres of pressure. Now we simply plug this into a calculator and we get that the final temperature, the new temperature T2, is 86.7 degrees Kelvin. Another example would be taking the speed equals distance divided by time formula that we just showed on the previous slide and putting in numbers for two of those three values. So in this case, we have a speed of 3.5 meters per second. We have a distance of 6.8 meters, and our time is our unknown. Well, we solve for time by doing a cross multiplying. The 3.5 is multiplied by the t, and the 6.8 does not have a partner. So we rewrite that as 6.8 meters equals parentheses 3.5 meters per second times our unknown time. Well, to solve for time, we have to take that formula, divide both sides by the 3.5 meters per second. Those cancel each other on the right side of the equation this time, and we're left with time equals 6.8 meters divided by 3.5 meters per second. And we get a number value of 1.9, and the unit is in seconds since we're talking about time. So this is how you use the cross multiplying once you've already put numbers into the formula, but you haven't taken care of the fractions. And then finally, kind of an advanced use, once you're used to using cross multiplying and you've done it over and over again, and you always know that it's the numerator 1 times denominator 2 equals numerator 2 times denominator 1, after a while you'll see a pattern here. And I've got an example with the same numbers we just looked at on the left side of the previous slide. 45 atmospheres of pressure divided by 325 degrees Kelvin equals 12 atmospheres of pressure divided by our unknown temperature. Well, We could do the cross multiplying. Blue times blue would give us temperature times 45 atmospheres. Or we could realize that, hey, all we're going to do is cross multiply, and then we're going to divide by the one extra that doesn't have a partner. So in this case, that means we're going to multiply 325 degrees Kelvin times 12 atmospheres of pressure. That's normal. But instead of setting up an equals sign with the other pair, we'll just divide by the 45 atmospheres directly and get our answer in one setup step. So now we have our formula, and we just plug it into our calculator, and we get our answer directly of 86.7 degrees Kelvin. And with that, we'll stop here.